Okay, so this is a set of notes on what are models and why are they useful. I'm going to do this straight from the notes because there's a lot of diagrams and pictures in here that may be hard to do if I do it off the black screen, so we're going to work with this. A model is usually either a physical object that's like in 2 or 3 dimensions, or it can be some sort of abstract representation. So it can like literally be graphs or equations, things like that. Um, Sometimes they represent a person or a thing or a proposed structure. Most often than not, it's a proposed structure, like a system in engineering. Could be a system of people, though. It could be a system of things. In this case, the physical models are usually smaller than the actual structure, because like building a model the same size as the structure is kind of redundant. But they definitely have a low lessening of complexity as well. So descriptive models are things that show the relationship between parts and wholes. So an example of this would be something like a parts tree. So kind of minimize that a little bit so you can see more of it. But you've got a some sort of mechanical reality here, and they're showing you how all the parts of it string together by building some sort of tree diagram. This is what we would call a parts tree. Another type of descriptive model is a mechanical drawing. So these are things that we're actually going to be working with in class. We might not do any mechanical drawings that are this complex, but this is somebody's work to try to show some sort of valve system and how its parts are strung together. Another thing that you could have is an actual 3-dimensional model where somebody goes and builds a smaller size version of the actual system that's going to be built. So here we have a 3-dimensional model of what would be an enormous bridge, so that somebody can actually take a look at that and make some measurements and try to draw some conclusions. Not all models are physical like that or descriptive. Some are analytic. An analytical model is a model that uses mathematical relationships, usually differential equations, to support a system. They're used to reliably predict how the system will form. I believe these are the equations that describe the behavior of light in a physical system. So they're a bit complex, but they're multivariate differential equations that can be used to draw conclusions about how light would perform within a system. Another thing that's commonly used are things called simulations. Simulations are where we actually use something that's a completely different system from the one that we're studying, but will reliably produce the same outcomes using the same as the one that's trying to be modeled. So here is an example of a Monte Carlo simulation where somebody has done trying to use mathematics to try to see what would happen within a system over time. So they started off at some random different point and watched what would happen as it went forward in time following a simulation of that system. And you can see like there are some outliers in the different curves that are here, but most of them are bunched up around a central reality, and that can give the engineer an idea of what are like the expected or tolerant ranges of outcomes that could happen using that system that's being modeled by this. You also have computer simulations. You guys hit one of these when we went down to Virginia using the flight simulators. So flight simulators are computer simulation. You're not actually flying the plane. You're looking at a computer screen that is showing you basically what you might, an image of what would it look like if you were looking, out of the screen of the airplane. But this is a computerized version that gives the same outcomes as the plane would actually do without actually having to strap yourself into the plane. Why do we use models? First, usually the models are cheaper in dollars or quicker to build in time. So that's an upside to things. Oftentimes models can be something that's safer than running the actual system. Like, think about this. If we had put you in actual airplanes, some of you would be dead today. So the simulation gave us an opportunity to be able to see what would happen if we were flying the plane without actually crashing the plane in an unsafe way. Precision. So sometimes it's very difficult to make a precise measurement on a full-scale working system, but if you have a model of it, you can take the measurements a little bit easier because either the model's smaller or less complex. And portability. I mean, like, you can move things around within the model, but also you can move the model itself from location to location much easier. Much easier to move the model of the bridge than it is to move the bridge, right? So that's kind of the 4 big gains you get through modeling: cost, safety, precision, and portability. The drawback is that every model is an incomplete abstraction of the system. So there's always there's always aspects of the system that you're not going to see in the model. You know, like, at the end of the day, if you build a model of a bridge, you don't get an idea exactly of how the dead loads are going to work in there because the model is much lighter than the actual bridge. Or, when you're using the flight simulator, you may not understand exactly what does it feel like to be in the cockpit of the plane when an enormous gust of wind comes across your little Cessna airplane. So you have to remember that there's measurements that can be lost there. And a common error is assuming that a measurement it can be transferred from the model to the system that cannot. Just because you can build the model of the bridge and have it stand doesn't mean that the actual bridge itself will stand. Modeling then is ultimately an abstracting or scaling down of a system. It's an important part of the design process. Typically models are used because they're less costly, safer, easier to measure, and portable than the actual system. The downside is that not all of the measurements that you can take of a system can be reliably transferred from a model. All right, so there you go. So there's your overview of modeling.